All right, let's talk about two words you hear all the time in image processing and deep learning: correlation and convolution. They look almost the same, they act almost the same, but there's one tiny, absolutely crucial difference that changes everything. Let's dig in and figure this out.
So what is the real difference? On the surface, both of these operations seem to be doing the exact same thing. But where you use them, well, they're worlds apart. We're going to solve this little mystery right now, and by the end, you'll see exactly why that small change is so incredibly powerful.
You often see this in textbooks, a hollow star for correlation and a filled-in star for convolution. And it's a pretty good way to think about it. At a high level, they share the same basic process, but one is all about finding a pattern, while the other is about creating an effect.
To really get this, we've got to start with what they have in common. Think of them like confusing cousins. They look alike, they sound alike, but they have totally different jobs. So let's unpack the process that they both share.
Okay, so the basic mechanic for both is this. You take a small grid of numbers, usually called a mask or a kernel, and you just slide it over a bigger grid of numbers, like an image. At every single spot it lands on, you multiply the numbers that line up and then add them all together. It's kind of like a sliding window that does a quick calculation at every single stop.
Let's start with the one that's a bit more intuitive: correlation. I mean, the name itself is a huge clue, right? Correlation is all about measuring similarity. Its whole job is to find out where a specific pattern exists in your data.
Simply put, correlation is trying to answer the question, how much does this little patch of the image look like the template I'm searching for? A high score means a great match, and a low score means, well, not so much.
Let's see this in action. We take our mask and place it right over the top left corner. We multiply the corresponding numbers, add them all up, and boom, we get our first output value, 129. Simple as that. Then we just slide that mask one step to the right and do the exact same thing all over again. Multiply, add, and we get a new value. And whoa, notice this one is 226. That's way higher. It's basically telling us there's a much better match in this spot.
And you guessed it, this just keeps going. Sliding across, sliding down, position by position, until we've covered the entire image. Each little step gives us one new number for our final result.
So what we're left with is this brand new matrix, where every single number tells us how well the mask matched up with the image at that exact location. We've basically created a map of similarity.
So why do we care? Well, template matching. Check this out. The input image has a bunch of letters, and our template, or our mask, is the letter D. After we run the correlation, look at the output. You see those bright spots? The brighter the spot, the better the match. It's pointing right at the D. That's correlation doing its job perfectly.
Okay, on to convolution. It uses the exact same sliding window process we just saw, but with one tiny game-changing twist.
And here it is. This is the big secret. The only difference between correlation and convolution is that for convolution, you first rotate the mask 180 degrees. You flip it upside down and backward. That's it. That's the whole thing.
But that one simple flip has massive implications. It's what turns the mask from a template you're looking for into a filter that you're applying. This rotation is what lets convolution do all that cool stuff like blurring an image or sharpening it or detecting edges. It's not about finding something anymore, it's about changing something.
Okay, so we have the theory. Correlation finds a match. Convolution applies a filter. Let's put them head to head and really see the difference in action.
And the math actually tells the story beautifully. You don't have to be a math genius, just look at the very end of the formulas. For correlation, you've got f of x plus s, and for convolution, it's f of x minus s. That one little plus versus minus sign, that's the math version of that 180-degree flip. It completely changes how the operation works.
That flip also gives convolution some really important mathematical superpowers that correlation just doesn't have. It's commutative and associative. What does that mean for us? Well, it means with convolution, the order you apply your filters in doesn't matter, and you can even combine a bunch of filters into one big one before you start. That makes it way more efficient and powerful for complex effects. Correlation can't do that.
Let's trace the process right here. On the left, with correlation, the mask W slides across, business as usual, and we get a result. Now, look at the right for convolution. See that first step? The mask is rotated 180 degrees before the sliding even starts, and that one little change gives us a completely different result at the end.
And here it is in 2D, which is how you'd see it with images. In part C, we have our mask, we apply it, and we get the correlation result in D. But for convolution, look over at F. The mask W is rotated first. Then we apply it, and we get the convolution result in G. Same input, same original mask, but that one flip creates a totally different output.
Okay, so let's get down to the bottom line. Why does this all matter in the real world? It really comes down to their core purpose. One is for measuring similarity, and the other is for applying filters.
So here's your cheat sheet. If your goal is to find something, like find a face in a photo or a specific character in an image, you want to use correlation. But if you want to modify the image itself, like blur the background, sharpen the details, or find all the edges, then you need convolution.
And hey, here's a little pro tip from the world of AI. Those things called convolutional neural networks, a lot of the time their convolution layers are actually performing correlation. Why? Well, because the network is smart. It just learns the filter weights already flipped around. It's a neat little shortcut, but the goal is the same. It's acting as a filter to learn features.
Look, if you remember just one thing from all of this, let it be this. The mechanical difference, the nitty-gritty of it, is just that 180-degree rotation of the mask. It's such a simple change, but it has a massive impact on what the operation is used for. We've talked about images and AI, but these ideas are everywhere, from cleaning up audio recordings to modeling physics. So now that you know the difference between finding a match and applying a filter, where else do you think you'll spot these powerful tools at work?